Let's jump right into this explainer. Today we're unpacking some truly incredible and honestly kind of mind-blowing engineering. We're looking at a phenomenon that feels like it's ripped right out of a sci-fi movie, but it is 100% rooted in the very real, hard and fast laws of aerodynamics. Imagine for a second you're flying high above the clouds, and suddenly the physics that keep you safely airborne just turn off. I mean, the controls in your hands do absolutely nothing. It is a terrifying concept, right? Well, that's exactly the focal point of our explainer today, the T-tail trap and the engineering behind the deep stall nightmare.
So what exactly happens when an aircraft develops a mind of its own? To really grasp this, put yourself in this scenario. You're cruising comfortably in this sleek rear-engine business jet. You look out the window, you see a beautiful, clean wing, totally free of those massive, bulky engines. But then, the nose of the plane begins to pitch up, higher and higher. The pilot frantically pushes the control column forward, practically begging the nose to come back down to the horizon. But the plane, it just ignores the command. Literally, it feels exactly as if the aircraft has developed a mind of its own. It's suspending the rules of reality and entirely ignoring human input.
Okay, let's dive into this. Because what you're experiencing in that scenario is what engineers and pilots call the deep stall nightmare. And you know, this isn't a mechanical failure, it's not a computer glitch, it's a highly specific, rare aerodynamic trap that is actually the direct result of a calculated engineering trade-off. It's a bizarre situation where the laws of nature seem entirely suspended, trapping the aircraft in a state that it just cannot simply fly out of. To understand how exact calculations keep us safe from this, we really have to deconstruct the physics at play.
Section 1. Aerodynamics 101. Understanding stalls.
Before we can wrap our heads around the nightmare scenario, we need to quickly look at how a regular, run-of-the-mill stall works. Every single airplane in the sky is governed by one absolutely critical metric: angle of attack. Simply put, this is the angle between the airplane's wing and the oncoming air. As a pilot raises the nose, that angle increases and lift increases right along with it. But there is a hard limit. If that angle gets too steep, the smooth airflow traveling over the top of the wing just can't stay attached to the surface anymore. The flow separates, the pressure distribution completely collapses, and boom, you lose your lift. That's your standard stall.
Now, in a normal airplane, let's picture your standard Boeing 737 with those big engines slung right under the wings. The recovery here is incredibly straightforward. The airflow separates, lift drops sharply, and all the pilot has to do is push the nose down. Actually, scratch that. It's really that simple. By dropping the nose, gravity helps the plane regain airspeed, the air reattaches to the wing, and you simply fly right out of it. The horizontal tail at the back of the plane has plenty of clean, fast-moving air to push the nose down when commanded. It's a simple, reliable law of physics.
Section 2. The T-tail trade-off. So if a standard stall is so easy to recover from, why change the design at all? Well, contrast a standard airliner with a modern, sleek business jet, and this brilliantly illustrates the difference. With a traditional airliner, you've got engines under the wings and a standard tail section right at the back of the fuselage. But with a sleek business jet, say the Gulfstream G650, the engineers completely moved the engines off the wings and mounted them to the rear fuselage. And consequently, they had to take the horizontal stabilizer, the little wings at the back that control the up and down pitch of the nose, and mount them all the way up at the very top of the vertical tail fin.
Now you might be wondering, why willingly make this drastic change? Well, engineers make this trade-off for a few incredibly compelling reasons. First off, moving the engines gives the plane clean wings, which drastically improves aerodynamic efficiency. Second, without those massive engines hanging under the wings, the plane can sit much lower to the ground. That's absolutely perfect for deploying built-in stairs at smaller private airports. And finally, because those jet engines are now mounted right on the back of the fuselage, you literally have to move the horizontal stabilizer to the top of the tail fin, creating that classic T shape, just to keep it out of the blistering hot engine exhaust. It's an elegant, beautiful design.
Section 3. Blanketing the tail, the physics of the nightmare.
But here's where the tension really ramps up. This beautiful, elegant T-tail design, it creates a hidden, terrifying trap when the aircraft enters a high angle of attack situation. Now, what's really interesting about this slide is seeing exactly how the disturbed airflow traps the aircraft step by step. Let's look at step 1. The plane pitches up way too steeply and the main wings stall. But unlike our standard airliner, the stalled main wing isn't just not producing smooth air, it creates a massive, turbulent wake of violently disturbed airflow. In a standard plane, that wake passes harmlessly above or below the tail. But with a T-tail? As the plane pitches up, that massive blanket of turbulent air moves directly, squarely over the high-mounted horizontal stabilizer. And that, well, that leads to the ultimate loss of control.
At this point, the elevator becomes completely useless. It's locked in a flat, falling attitude. Think about the physics of this physical state for a second. The elevator at the very back of the plane is the exact tool the pilot needs to use to push the nose down. But because it's entirely engulfed in the chaotic, turbulent wake of the stalled main wing, there's absolutely no smooth air moving over it to generate any aerodynamic force. You push the control stick forward, and sure, the elevator moves, but it has literally nothing to push against. The plane is just trapped in a flat, falling state.
It's incredibly scary. As aviation safety reports chillingly note, the aircraft is no longer listening to the pilot. Recovery from this deep stall is nearly impossible. The pilot is essentially trapped inside a machine that is plummeting out of the sky, completely ignoring all inputs. Why? Because the aerodynamics required to save the plane are being actively blocked by the plane's own structural design.
Section 4. The engineering solution.
Naturally, this raises a massive question, right? If this literal death trap is hidden inside the physics of the T-tail, why on earth do we still fly these planes? Why are they some of the most popular business and regional jets in the entire world? Well, because engineers are brilliant problem solvers. So, the crucial point is this. Aviation is all about layered redundancy. Engineers didn't just cross their fingers and hope pilots wouldn't pitch up too high. No way. They used exact calculations and a deep respect for the laws of nature to create a brilliant, albeit incredibly aggressive workaround. They acknowledged the trap, and they engineered a foolproof way to ensure the airplane could never, ever fall into it.
The answer is a brute force solution known as the stick pusher. And let me be clear, this isn't a gentle warning light or a subtle little vibration. The stick pusher is an automatic protection system that acts as the ultimate safeguard. It utilizes an incredibly powerful hydraulic actuator connected directly to the pilot's controls. If the plane thinks you're about to enter that nightmare scenario, well, this system takes physical control away from you to save your life.
Let's move to and see how this builds, how this automated safety sequence actually plays out in real time. On the outside of the plane, sensors are constantly, relentlessly monitoring the angle of attack. They feed all this data straight to the flight computer. The very instant the computer detects that the plane is approaching the dangerous angle, the precise degree right before a deep stall can happen, it doesn't just buzz a warning. The hydraulic actuator instantly and violently forces the nose down automatically. It physically slams the control column forward right there in the cockpit, overriding the pilot and pitching the nose safely down before the turbulent wake can ever blanket the tail.
It's a system that is orchestrated down to the very second. And it's just a beautiful reminder that in aviation, absolutely nothing is left to chance. This safety mechanism is exactly what allows us to safely enjoy the incredible benefits of the T-tail. The significantly quieter passenger cabins, the sleek aesthetics, and those incredibly efficient clean wings. The stick pusher tirelessly works in the background to ensure we are kept safely out of the coffin corner of aerodynamics.
I am genuinely fascinated by how human engineering has mastered these hidden, almost invisible dangers in the sky. By understanding the strict limits of physics, we've designed machines that protect us from the very flaws we built into them. But I want to leave you with the provocative thought based on everything we've explored today. The next time you see one of those sleek private jets sitting on the tarmac with that high T-tail, do you see a masterpiece of efficiency managed perfectly by layered redundancy? Or does knowing the physics of the deep stall nightmare make it feel like a scary aerodynamic trap? It's a fascinating balance between risk and reward for sure. Thank you so much for joining me for this explainer, and I hope it leaves you curious to uncover even more of the hidden physics that shape our world.